All right, so next up is the concept of, well, there's a few concepts in here, but we're talking about parts of a circle. So chords, arcs, central angles, those different types of arcs. We have major arc, minor arc, central angles, like I said. Yeah, a bunch of different things going on here. A minor arc, any arc that's less than 180 degrees is going to be considered a minor arc, right? So the central angle is formed with its vertex at the center of the circle, whereas the major arc is greater than 180 degrees. So you can see in the diagrams, so it's pretty straightforward. The one key ingredient there is that the minor arc, it's less than 180 degrees, but generally it's going to be equal to the central angle, right? So it doesn't necessarily have to be the central angle, but it should have the same measure as the central angle, right? So that's a little bit of a twist on the concept, and it could be a little mind-bending, but it's not generally overwhelming. All right, so really just getting a sense of the terminology can be somewhat daunting, but it's an acquired taste. Once you get used to it, it's fine. In a circle, the diameter that is perpendicular to the chord bisects the chord and its arcs. All right, so that's a relationship. A diameter that is perpendicular to a chord. So a chord is a line segment that passes through a circle, right, but doesn't extend beyond the circle. So, like, for example, A and B, that's a chord, all right? It's like, a diameter is an example of a chord, right? But it's not the only chord. So any line segment that connects 2 points on a circle is going to be a chord. Q and S would also be a chord, Q to S. So a diameter that's perpendicular to a chord bisects the chord and its arcs. All right. Now, a radius is half of a diameter, so the radius would also accomplish that same objective. All right. So it's going to bisect the chord and its arcs. That's why, so you have CR, let me get my highlighter. I'll use a highlighter. CR bisects QS, and you can see how it becomes 7 and 7, all right? Or at least it was 7 and 7. So we have X and X. I don't know what these two guys are. And we're going to need to know what those are in order to figure out what the whole length of AB is. So that's coming up. That's going to be part of the fun, all right? So that's where we're at. So what can we do? Well, I can create right triangles, right angles, right triangles. I like the sound of that. Do this in red over here. I might have to hand draw that one. Kinda. Yeah, it's pretty much there. That's enough to go with it, I guess. All right. So what can we do? Well, we could figure out what the radius is, right? Because 4 squared plus 7 squared is going to be equal. I'll use R for radius. All right. So 16 plus 49 is going to be equal to R squared. So 16 plus 49, so 59, 65. So that means R is going to be equal to the square root of 65. All right. So that's what this guy is going to be. Now, we're looking at, because again, all radii are congruent to one another, we're looking at two triangles that are going to end up being congruent. All right. So how do I know they're congruent? Well, there's a couple of ways. But One way is that it's the hypotenuse leg theorem. The two triangles are congruent. All right, so I'll highlight again, but different color. So, well, the altitudes are the same. Those are legs. We just discovered that these hypotenuses are going to be the same. So therefore, x has to be equal to 7. All right. So if two triangles are congruent, then their corresponding parts are congruent. All right. So therefore, x is equal to 7, and AB, line segment AB, and actually it's measure, use the proper notation, would be equal to 14. All right, and so I'll take it as a typo for number 6. Find the measure of segment AB. All right, so using that same idea in the next one, we could actually kind of go the same way, right? If we know that it's going to be a bisector, if we know it's going to split it into congruent parts, that x is going to cut that 36 in half, and we know that we're dealing with congruent triangles from the last units, then whatever the altitude is for one is going to be the altitude for the other. So therefore, x, poor quality x, because I have the line draw tool on, x is going to be equal to that altitude, which is 16. All right. The perpendicular bisector of a chord contains the center of the circle. Wonderful. Find the length of the chord and the distance from the midpoint of the chord to the midpoint of the minor arc. All right. The length of the chord, that's x. We know that we have a Pythagorean relationship here. So some value here, I'll call it, let's be a little bit more adult about this. We'll call that a. So a squared plus 4 squared is going to be equal to 6.8 squared. A squared plus 16 is going to be equal to, get my handy dandy calculator out, 6.8 squared, 46.24. Now we're looking at decimal values here, so, just ballpark it best we can, 30.24. And so so we're taking the square root of both sides. A is going to be approximately, so minus 16, 5.499. All right, so therefore, poor quality therefore symbol, x, which is going to be double that, is going to be approximately 10.998. All right, so we have that. So it's find the length of the chord, good, and the distance from the midpoint of the chord to the midpoint of its minor arc. All right, so we want to identify the minor arc. Pen just turned off. That's going to be this guy right here. Oop. That's going to be much easier to do, all right? Because the radius of the circle is equal to 6.8. So that's this whole distance here. I'll use a dashed line. And we already know that we've traveled 4 units. So we're at 2.8. That's the distance from the midpoint of the chord to the midpoint of the minor arc. All right? So I'm just going to use a highlighter because that's going to be a lot to write out. Distance, all of that is going to be this. All right. Next up is a concept called an inscribed angle. All right. An inscribed angle is a point that's on the circumference of a circle that opens up onto the circumference of the circle when you create an angle through it. All right. So that measure, that inscribed angle is always going to be half the measure of the intercepted arc. Those arcs are generally measured in, well, they're angular measures. They're generally measured in degrees. Sometimes they're measured in radians, which is another way of measuring angles that we're not going to really focus on. But just so you know, all right. So the measure of an inscribed angle is half the measure of the intercepted arc. The measure of an angle formed by a tangent and a chord is half the measure of the intercepted arc. And that's because a tangent and a chord create something that ends up being kind of like a facsimile of an inscribed angle. Right? It gets the same point across, gets the same job done. So we'll play around with that a little bit. But when it says find x in number 9, it's like, well, they didn't give us enough information. They actually did. They told us that all sides of this triangle are congruent. If all sides are congruent, then it's equilateral. Let me thin this out a little bit. If it's equilateral, then each angle is going to be 60 degrees. So if angle, the measure of angle ACB is equal to 1/2 x, then we know that 60 degrees is equal to 1/2 x. Half of what is equal to 60? Half of 120. But you could also just, if you want to do it like an equation, multiply both sides by 2. 120 degrees is equal to x. All right. Here it's saying find x, but x is not the referenced angle. Well, it is the reference angle. It's not the inscribed angle is what I meant to say. That inscribed angle should be 100 degrees. And we know that there are 180 degrees in a triangle. So 180 minus the 100 minus the 40 that was given. So we're looking at 40 degrees. And so that's x. All reliant on that piece of information about the inscribed angle. Now, obviously, this is a busy looking diagram in number 11. RS and TU are diameters of circle A. RS and TU, if you just look at them, look carefully. Try not to get overwhelmed by the picture. That's one of the big challenges when it comes to this stuff. Here's RS. Just look at it a piece at a time. TU are diameters of circle A. RB is tangent to O at R. All right, so we're looking at a tangential relationship, which means that, like all fancy terminology aside, it's telling us that there's a right angle there. We need to find angle BRT and the measure of angle TRS. All right. Now, one thing that we do know from a couple units ago, a couple lessons ago, is that vertical angles are congruent. So here's 126 degrees. And consecutive angles, when you have an intersection, they're going to be supplementary. All right. So these angles here, I'll just make a little note, are going to be 180 minus 126 degrees. So that's going to be 54 degrees. A lot of this stuff ends up being just take a look at the picture and see what you can figure out. All right. It's a good place to start. All right. We already know that we have a 90-degree angle here, but now that 90 degrees is that marking is looking way too big. I want to make that look a little nicer. So we know, well, not that it looks much nicer, but it is what it is. So we know that we have the 54-degree angle. We can also figure, and the 126-degree angles, we can also figure out things like the intercepted arcs. So we know that this angle here has to be this arc has to be 54 degrees. I'll highlight it or mark it up. you know what? Let's go blue. For those keeping score at home. And so this is going to be 54 degrees. The intercepted arc is going to be the same. All right. We also know that, let's get a little green in there, that this guy here, oh, shaky hand, is going to be 126 degrees. All right, and that accounts for half the circle, so we know we're up to 180, which should make sense. Now here's the little twisty part, and it's interesting, but it can be a little weird because if you don't see it immediately, it can be kind of frustrating. This angle here, let's go, this guy right here is going to be 63 degrees. Because while 126 is the intercepted arc for the central angle of 126 degrees, it's also the intercepted arc for the inscribed angle of 63 degrees. And the inscribed angle is always half the intercepted arc. All right. So from there, you know, same general idea, we know that this has to be 27 degrees. All right, because again, we're looking at an intercepted arc. That 54 degrees is the intercepted arc for the central angle of 54 degrees, but it's also the intercepted arc for the inscribed angle of 27 degrees. All right? So we can pull a lot of meaningful information out of this. And so we can get another angle here just by doing 180 minus 126 minus 27, which is going to be 27 degrees. All right, so I'm still in the part of the process where I'm like, oh, let's just write down everything I know. Now, just going back for a second here, they told us indirectly that this is a right angle. So if that's a right angle, and you know that part of it is 60 degrees, then the other part of it, and these diagrams get very, very busy very quickly, that other part of it has to be 90 minus 63. So 27 degrees. And that kind of doubles based off the fact that if you look at one of the relationships above, the measure of an angle formed by a tangent and a chord is half the measure of the intercepted arc. So here is, and I'm gonna scribble it in and then I'm gonna erase it. Here's a tangent. Here's a chord. It's going to be half of that intercepted arc. The intercepted arc is 54 degrees, so that makes that angle in there, that one that's tucked in there, 27 degrees. All right, so there's a lot going on with that, but at long last, we finally get at an answer, 27 degrees. As soon as I get my penda function, 27, make it thicker again. Now the other one is TRS, and it's kind of interesting because, you know, like you do all this work and sometimes you go right past the answer that you're looking for without even realizing it. TRS, we already figured out, is 63 degrees. All right, so definitely a lot more complicated than the first page, but if you take some time to really consider what's going on, I think it'll make